Welcome everyone. In this video we will derive a formula for finding the derivative of the quotient of two functions. So the question that we are asking is, if we have h of x divided by g of x, and if we take its derivative with respect to x, what is this derivative? Now, you may want to say that this is a simple question. We will just take the derivative of h of x, take the derivative of h of x, and then take the derivative of g of x. Then we will divide both of them to get the derivative of the quotient. Well, no, we can't do that, and let's see why we can't do that. So first, let's define a function f of x, and we are defining it as h of x divided by g of x. So we define f of x as our quotient. Well, let's do a dimensional analysis. So we will use the units. For example, let's assume h of x is in meters squared and g of x is in meters, which means f of x is in meters, right? Meters squared divided by meters, that's just meters. So if we take the derivative of both sides with respect to time, we would get the derivative of f of x, which is f prime of x. This would be, well, actually this is not a right way of saying it. Let's say if we were to take dt of f of x, we would get, as the unit, we will get meters divided by seconds, right? We would get meters divided by seconds because f of x is in meters and time is in seconds. So if we take the derivative of the other side, which is, let's do it like, we have h of x divided by g of x, and maybe we're taking it with respect to time. Well, and dt here. Well, in this case, if we take the derivative of the top, we would get meters squared divided by seconds, and the bottom would give us meters divided by seconds, which is meters divided by seconds squared. So clearly, even the units does not work, which shows us that this is not equal to the quotient of the derivatives. We just cannot do this, and we were able to see a reason why we can't do it by a consideration of the units. So let's do it the right way. And to start our proof, I will write the definition of derivatives. So the derivative of f of x would be the limit as delta x is approaching 0 of the quotient f of x plus delta x minus f of x all divided by delta x. Alright? Now, if we look at this term, f of x plus delta x, this is simply meaning that we were at an initial f value, and due to the change in our x, we ended up at another f. So we had a change in our f, which is delta f. And if we want to express it in terms of h and g, because remember, we made up f was not given, we defined it, so we should convert everything to h and g's. So if we think of this in terms of h and g, it will simply be h plus the change in h divided by g plus the change in g. And notice I omit writing the parentheses. For example, here I didn't write the f of x just to make it short. You should think of whenever you see f, h, and g in this context, you should think of them as functions. They are not variables, even though I don't put their arguments anymore. So this is all great. And if you look at the second term, f of x, well, this will be just f. We were at an initial f, and we stayed there. There is no change. So by our definition, this will be h divided by g. Great. So let's substitute these two formulas that we found for the two terms that are in the numerator. And I will do that on a new page. So we have, for f of x plus delta x, we have h plus delta h divided by, well, let's see, divided by g plus delta g, and minus h divided by g. And remember, we had a delta x in the denominator, so I put that one as well. Now notice that since I didn't put a limit in front of this expression, this won't be equal to the derivative of f of x. This won't be equal to the derivative of our quotient, but it will be approximately equal to the derivative. And at the end, when we take the limit as delta x approaches 0, this will be exactly equal to the derivative. So if we continue, I want to collect the numerator under one denominator. So I will multiply, I will do this. I will multiply by g and g here. And I'm going to multiply with g plus delta g and then g plus delta g here. Okay? This is just multiplying by 1. So we can do this. This is what I am doing. So we get g h plus delta h, and we have a minus, right? Watch out the minus here. Minus g plus delta g multiplied by h divided by our common denominator, which is g times g plus delta g. Also, we have another division. We have delta x, so let's just put it here as well. We have delta x. This is all great. I just combined the different terms under one denominator to make it simpler. Now, this is equal to, if we now divide by delta x, the terms in the numerator, we would get g h delta h, and I am dividing by delta x, so I will put divisions like this. Let me write it one more. Let me write it again. So we divide by delta x, and I am dividing what is inside the parentheses. I distributed the division inside the parentheses. Then we have a minus. Again, I am dividing what is inside the parentheses. Delta g divided by delta x times h. This is divided by g plus delta g. And notice we do not have another delta x in the denominator because we already divided it as we did it like this. So this is great. Now I want to open the parentheses and let's see what happens. So if we distribute g in the first term, we get g h delta x plus g delta h delta x minus g. Now we are just distributing the h, so gh divided by delta x. Now don't forget, you also need to distribute this negative sign, this minus sign. So we have a minus delta g h, which is divided by delta x. And all of this is divided by g times g plus delta g. Well, notice a great thing here. If you look at this and this, they are the same, only their signs are different, so they cancel each other. And if we now take the limit, actually let me do it on a new page, on the next page. So we had g delta h divided by delta x minus, let's see what we have. We have h delta g delta x all divided by g times g plus delta g. Now I am interested in taking the limit of this thing. Limit, and where did I write it? Come on. We are taking the limit as delta x approaches 0. And as I said, if we take the limit as delta x approaches 0, this will give us the derivative of f. This will give us f prime of x. So, if we take delta x to 0, this thing right here, by the definition of a derivative, this will give us h prime of x. This is h prime. And this thing right here, that is going to be g prime. Okay? Because remember, another definition of derivatives is that f of x is equal to the limit as delta x approaches 0 of delta f divided by delta x. Alright, we are using this idea here. And another point is, as delta x approaches 0, delta f approaches 0, well, not delta f actually, let's do it like this. As delta x approaches 0, delta h approaches 0, and delta g approaches 0 as well. So, when we take the limit as delta x approaches 0, this thing right here, delta g, it will go to 0. Which leaves us with the statement that f of x is equal to g times h prime minus h times g prime divided by g squared. Well, what was f? How did we define it at the beginning? If we go back, we defined f as follows. So the derivative of f of x is simply the derivative of the quotient that we were since the beginning interested. So this is the result is, if you have a division of two functions, a quotient of two functions, to get their derivatives, what you do is you take the derivative of the first function, the one in the numerator, you multiply it with the second function, the one in the denominator. Then you have a negative sign. You now take the derivative of the function that is in the denominator and you multiply it with the numerator. Then you divide it by the function that is in the denominator. So this is the derivative of the quotient of two functions. We just proved this formula. We derived it. I hope you found this video helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.